Okay, so we start again in a moment. We're trying to change a speaker. No, va bene, ma se parli, if you speak loud, I think everybody. Ah. Vedo che ammetto. Ok. E adesso provo a fare share. We're almost there. Ah, io non lo vedo, cara.
No.
Ah, ok. Join. Join, devi cliccare. Yes. All right.
Allora, ciao a tutti, mi sentite? Can you hear me?
Aspetta, però, forse...
Allora, lì togli il volume, perché sennò c'è rientro, no? Penso di sì. Cioè, metti il volume al minimo.
Quando ci riesco, non sono capace.
Ma
Okay. You can go? You can go. Now the second part of the lecture.
can you hear me?
Yes.
Okay, thank you, Margherita. So, okay, share screen. I'm not used to Zoom, so let me check this. Share. Okay.
It's working perfectly.
Right?
It's working perfectly.
Okay, but what if I want to share something different?
Okay, you need help?
I'm sharing. Let me try. Okay.
Also log yourself in this device, right? So you could, or you can do that. Okay.
How can I remove this bar?
This I can.
Oh.
This I really cannot.
Okay, this way. Okay, okay, so you can see this. Hide, okay. This one I'm doing. I think I'm fine. Okay, so I can switch in this way, and I can take this away. Okay, is the recording going on?
Everything is on. It's on you.
Okay, it's very nice. You can see my setup, but I have 3 laptops in front of me. Now I'm looking at you in the main laptop with the Zoom connected. Here I'm looking at my cheating laptop, that means where I have my secret slides that I can read without looking as I reading something. And over there, when I turn this way, it means I'm looking at the slide where I am writing something, but doesn't work here. Okay, the pen is not, oh yes, it is working, but oh, I hate this technology. Not really, because the pen is not focused on the display. Okay, maybe I will use the blackboard. And there is a terrible delay. Okay. Okay, I will do my best with this. Okay, I will do my best with this kind of technology. You can see the yellow dots moving. Yes, you can see on the beamer, but here not moving in the Zoom. Is the yellow some circle moving at home?
No, it's still. It's still up, just
Okay,
under
so we
recommended.
don't have interactions with the display. Okay, let's try this way. Okay, first of all, this lecture will be very different from Rita's lecture, meaning that it is a lecture much more high level, sort of a philosophical lecture. Well, you can tell me later. The first slides are almost philosophical. And moreover, the format of this lecture is very strange. I will comment slides, a composition of slides that are extracted from slides that are not mine, because if there are already the perfect slides in the internet, I don't want to try to reinvent the wheel. And so I will use slides and topics extracted from this course. You can see here in the first disclaimer slide, the course that is highly recommended by me to you to read, to listen to, is a course on geometric deep learning, and the authors are the founders, the authors of this beautiful theory, geometric deep learning, and these are their names. The course is on a playlist that you can see here. I will pass to you all the slides. So again, as Rita said, no need to taking notes. And okay, this is the original disclaimer. So my slides are a composition from 17 lectures of 2 hours each. Okay,
I'm sorry, Maurizio.
From these lectures, I extracted 60 slides, and I will not show all the 60 slides in 1 hour until right now, of course. So this is a very condensed lecture coming from a 17 times 2 hours long course. Okay, so for this reason, don't expect too many details. Don't expect details. Don't expect too much in general. But I will strive to give you the idea of what geometric deep learning is beyond graph neural networks. Because first, the elephant in the room. I'm sorry, Rita. Shut off your.
No, I was
Don't listen to me.
There was a problem.
Okay. Geometric deep learning is not graph neural networks. Okay, graph neural networks are a particular instance of geometric deep learning. Geometric deep learning is a much bigger, wide idea that is a beautiful idea, and my intent in this lecture is passing this idea to you. Okay, so that's done for the first slide. Of course, everything starts from here. So this is also the starting paper that Rita has mentioned to you, I guess, several times. And I strongly suggest you reading this. Every source I mention in this lecture, every citation I give to you is not a citation just to cite something, but it is a citation meant for you to be read. And with this, I mean also that I think you can read it. Okay, don't think these are beyond, not only beyond Euclidean data, but beyond your ability to understand it. This is perfectly readable. Okay, you can understand. Of course, not if you want to go into the finer details, but the general idea, you read it, you have the idea. Okay. So what's happening? What is this slide? This is the first of the philosophical slides I was telling you. You know, there are several geometries. I understand you are all mathematicians? Yes, okay. So you know there is hyperbolic, elliptic, Euclidean, affine, projective geometry. There are several geometries, okay? And today you know what a geometry is. But in the beginning of the last century, in the 900 or 1900, there was a mathematician, Felix Klein, that was asked to give a talk for his PhD dissertation, I guess. And he gave this beautiful talk that passed to the history as the beginning of the Erlangen program, where he said what thought a geometry was. Okay, so in the beginning, there was a mess in mathematics. There was so many different point of views. There was not the word geometry in the sense we mean today. There were several point of views, and there were people saying, oh, this point of view is better than this. This point of view is most important than this other point of view. And then Klein said, look, it's not the point is not what is the better geometry. The problem relies in what we are interested into. If we are looking at the problem, what are the symmetries up to which we want to study this problem? If I want to study polygons, am I interested in preserving the length of the sides, or am I interested only in preserving the shape of the polygon, or am I interested in preserving just other small features? If I am interested in lines, am I interested just in counting intersections of lines? You understand? If I just only interested in counting intersection lines, these two lines that I'm showing, I don't know, is it appearing on the camera? Oh, this is so difficult. Okay, if I move my fingers, I'm changing lines, but the point of intersection is always the same. So from the point of view of studying the intersection of these two lines, all these configurations are the same. But of course, these lines are different from what point of view? From the point of view of slope, from the point of view of other things. Okay, so with this observation, in that moment, the idea of what a geometry is was born. So a geometry is a group of symmetries. So this is the philosophical part. I want to convince you that symmetries are important. Symmetries are at the base of our everything. Imagine the situation. We are two friends and we talk to each other, and I ask you, what is your car? You say, oh, my car is a Ford Fiesta. And they say, oh, I have the same car. Is this the same car? I stole your car? No, it's, of course, I just mean with respect to the symmetries I have in mind in this context, in this setting, when we are talking and talking about natural language, I'm just telling you in a very nice, natural way that I have also a Ford Fiesta. Probably not the same color, since you haven't told me the color of your car, okay? So you see, I'm trying to convince you that the idea of symmetries, in this case, equivalence or relation of equivalence, no? Since we are mathematicians, equivalence relation, it's vital in every aspect of our life. It's not just a mathematical concept, okay? Symmetries exist, they live by their own lives. They are important in every field. Now, what's the meaning of this first four slides? The meaning is the following. The idea of geometric deep learning is that the principle, the guiding principle in geometric deep learning is that we are in deep learning now, 2016, we were a few years ago, in the same moment as we were in the
Maurizio, sorry, do you hear me?
How
Maurizio,
do you say XIX secolo in English?
sorry, can you hear me?
19th century. You're a genius. We are now in 2016. We were in the same moment as we have been in geometry in 19th century. That is, we are now starting to realize the importance of different geometries. That is, in deep learning, of different group of symmetries acting in our problem. As in geometry, the symmetries define your problem. You are interested in studying intersections, so the answer is projective geometry. This is the best. You are interested in distances and angles, then Riemannian geometry, Euclidean geometry is the good answer. And I'm not saying the second is better than the first one or vice versa. They live for different problems. Okay, so now the guiding principle in geometric deep learning is that when we face a problem, when we start trying to solve a problem, because this is what deep learning is, okay, solving problems. We have a problem, also called a task. We have a task. When we try to solve the task, we should first ask, what are the symmetries behind this task? And then, can we use these symmetries to make the solution to the task simpler? Okay, so this is what I will try to tell you to convince you. I will try to tell you what are symmetries in a most famous task, that is image recognition, and I will try to hint you how you can build models that are naturally compatible in some sense, in the equivariant sense, with these symmetries on this task. Okay. And as Rita was always saying, are there questions up to now?
Don't be shy.
Don't be shy.
Now,
in deep learning, well, deep learning, let's say it exists since, let's skip winters. Let's say deep learning exists since 2006, okay, which is the key date where backpropagation started to work. 2006, 2016, there are 10 years. Why in 10 years nobody thought that maybe symmetries were so important in deep learning? Because in deep learning, also the reason why it is so fascinating also for mathematicians, deep learning enjoy a beautiful theoretical property. This theoretical property is called, goes under the head of universal approximation theorem, which is not a theorem, but has several theorems, universal approximation theorems, that comes from the solution of a Hilbert problem, just to mention Kolmogorov and Arnold, that first solved this problem in the 60s. But just to be very sloppy, universal approximation theorem states that if you take a neural network fully connected, no convolution, no attention, no graph neural network, fully connected neural network, the worst neural network, the simplest neural network you can do, and you put at least one hidden layer. So I don't know if you call this neural network one hidden layer, 2 layers, or 3 layers if you count the input strata. Anyway, a neural network fully connected with 2 layers, as it's usually called, is able to approximate everything, every function you can imagine. Okay, you can build a neural network with 2 layers. Of course, you have to put a lot of nodes, a lot, but really a lot of nodes. But virtually, you have these theorems, mathematical theorems, that states that choose an epsilon of tolerance, and then if you put enough nodes in this neural network, in the hidden layer, you can approximate with tolerance this fixed epsilon essentially any function. These are theorems because there are theorems for continuous functions, there are theorems for measurable functions, and so on. Okay, so how is this related to what I'm telling you? Well, you could say why we should bother to care about symmetries on our problem and try to simplify our problem if we can just be blind, shut off our brain, build a 2 layers neural network, put in this 2 layers neural networks 1 trillion of nodes, and then we know that we can solve. There is a theorem that says that our problem can be solved by this architecture, by this neural network. Okay, so this is the question that I don't know if you have this in mind, but I want now to convince you that there is a difference from theory to practice. And this is true. What I said is true. But let's talk about another concept, another problem, which is called sample efficiency. Let's imagine the problem in which you want to classify pictures of cats and dogs. You have a lot of pictures of cats and dogs with a label, okay, with a good label that states whether in the picture there is a cat or there is a dog. And you want to perform a supervised learning, okay, you want to train a neural network, let's say this shallow neural network with 2 layers. And now you ask yourself, okay, I want to reach a certain accuracy. Let's say I want to reach accuracy of 1/10. That means that you want to train your network in such a way that after training, your learned function, your f hat, is distant from optimal function, the classifying function for cats and dogs, the theoretical function, is distant in a certain norm, you choose one, less than 1/10. Okay, so you want f hat minus f star in the norm minus then a certain epsilon. Now my question is, can you estimate how many samples, that means how many pictures of cats and dogs you need to be certain, in some sense, in some theoretical sense, to reach this approximation? Okay, this is my question. This question is called sample efficiency. I'm questioning myself about the sample efficiency of a 2-layer neural networks in approximating functions. Okay, well, the question is this one. How many samples are needed to approximate the function to accuracy, to a certain accuracy epsilon? Okay. Now, the answer is in this awful slide. Don't read it, please. Just look at the last lines, stating that if your data has dimension d, then the samples you need to be certain to be able to approximate your function with accuracy epsilon is epsilon to the power of minus d. Let's use numbers instead of epsilon and d. Let's imagine that our pictures are, give me a sloppy resolution for pictures of cats and dogs. 30 times 30. Okay, the NIF size. Okay, 32 times 32 is more or less 1000. Okay, so the dimension of this data is 1000. This is clear. Okay, the data, the picture is a vector of 1000 coordinates. And assume you want to reach a performance of 1/10, which is a awful performance. I mean, if you're really solving a problem, you probably want several magnitude orders lower. With these numbers, how many pictures of cats and dogs you need? 1 over 10 to the power of minus 1000. Revert. This is 10 to the power of 1000. This is way beyond the number of atoms in the universe. As you probably know, there are only 10 to the power of 80 of atoms in the universe. This is a huge number. And this can be synthesized in this beautiful slide that I put just to tell that I have cats and dogs, beautiful cats in particular in my slides, that there are not enough cats and dogs in the universe, not only on the Earth, in the universe, to solve this problem with the 2 layers neural network. So the theory states, okay, this is possible. But in practice, this is not possible because of this sample efficiency problem. Okay, up to now. So do you agree that it's worth your time, our time, to discuss possible solution to this problem? So first, let's investigate where is the problem. The problem in the theorem before, the way the theorem works in stating that you need at least epsilon to minus d samples to obtain your accuracy is because you are requiring a theorem that is able to state something without any additional assumption on the function to be learned. Think of it, the extreme case in which there is a very strong prior on the function to be learned. The function to be learned is a constant. Okay. Now, of course, you need just one sample. You show one sample and you obtain the constant value, and you know that using that prior, that hypothesis, that you know that the function solving your problem satisfy a certain property, we will call this kind of properties priors on the model. I don't know if you use this term. It's very, very nice. And so, of course, if we have hypotheses on the function we are looking for, on the task we are solving, you see, we are going back to the original principles. If we have this kind of hypothesis, then the problem is easier. Now, this is expressed in this slide in this way. If we know that the task is invariant to certain symmetries, a certain group of symmetries, and if we can make the neural network invariant to these symmetries, then the output is not anymore a function on the original domain. It's not anymore a function defined on the space of all the images, which is a space of 1000 dimensions. Okay, but it is defined, since you are a mathematician, can use this term, on the orbit space. The domain is cutted by slices, which are orbits. Every orbit becomes a point. Usually, this reduces the dimension. Okay, so this is a way to reduce the dimension of your problem. Okay. For mathematician, this is pretty. It's almost a tautology. It goes under the term group invariance theorem. Okay. Now, we have up to 6 o'clock, right?
Yes, actually, it should be 10 to 6 because
10 to
they
6.
pass out.
Okay. So now there are 3 slides summing up what is learning. I will not show this to you. And of course, we have the data, we have the error, we have the function we are trying to approximate. Okay, and we just show you a nice picture summing up all of this, which is this 1. Now, this is a messy picture, I know, but there are fundamental ingredients that are making things clear, I think. So in this picture, just look at this blue star, okay, F star. You can see the symbol. Imagine this is your target, your function you would like to know. Okay, this is the solution to your task. This is a function telling you whether, given any picture, the picture is a cat or a dog. Okay. Of course, you are never going to find exactly this function. This is clear. You want to approximate this function. In order to approximate this function, you choose a model. In this picture, the model is the yellow ball. The model is a set of functions. In this picture, the slide, the points are functions. Okay, so the yellow circle is full of functions. These are the functions, the only functions you look at, the functions between which you choose your solution, your estimate, your F hat. Is this clear up to this moment? Okay. What you do with deep learning is build a neural network. The neural network is a family of functions, right? Because there are parameters, so it is a parametric function. This family of functions is this yellow ball. And with stochastic gradient descent, with all that was said, you choose a certain value for the vector of parameters. So you choose a certain point in this ball. Now, what happens is that the point you choose is this purple one, this F hat. And this means that the error you make, called excess risk in the empirical risk minimization principle that I don't know if you talked about, but anyway, this is the error you are making. That is the distance between the function you would like to know, okay? And this error, you can see, is upper bounded by triangular inequality by two parts. These two parts are a statistical error and an approximation error. The approximation error is clear. It's the distance from your model, from the target function. You can't go closer than this with your model, okay? Because of the picture. Okay, I'm assuming in the picture the relevant measure is the Euclidean metric in the picture, okay? Just for the sake of clarity. But there is another part of error. This error is called the statistical error, which is given by the fact that you are not finding the minimum of the real loss, the population loss. You have a training set, and you estimate the population loss by a standard average, by an empirical mean. And this is what you minimize. Okay, so the difference from this and this is called statistical error, and it is due to the fact that the training set is smaller than the population, if you want to put this way. Okay, these are the two main parts of errors. There is a third part, because the optimizer counts, but statistical gradient, the stochastic gradient descent works so well that this third part you can ignore it. But what I want to tell you is that your error is doomed to be lower than the sum of these two terms. So you would like to make these two terms smaller. Okay. Well, there is a problem. In general, not always, but in general, if you enlarge the model, if you make this yellow ball bigger, you will reduce, of course, the approximation error, right? Because your model contains more functions. So you are getting closer in this ball-shaped picture. You're getting closer to the blue target function. But usually, the statistical error will become larger. Well, of course, if you have a bigger, more functions which choose, then minimizing on the same training set will get you an increased statistical error. So what I'm saying, in some sense, these two parts of the errors are conjugate. meaning that if one decreases, the other one is getting larger. So it seems that you cannot make this error smaller. Of course, this is not always true. Imagine making the yellow ball smaller, but not in this circular way, just removing functions that you are certain are not close to the function you're looking for. I mean, if you remove functions from the model, which are for sure not a solution to your problem, then you are not losing anything in terms of approximation error. So you are making your yellow ball smaller, but maintaining this approximation error. Because by hypothesis, you are not removing relevant functions. And of course, the statistical error is getting lower, it's smaller. Okay, so if you modify the model in a clever way, then you can make this step. You can make both error smaller. And this clever way, you can imagine, is again geometric deep learning, making your model invariant with respect to the group relevant for the task you are considering. Questions? Okay. So let me check this part. We skip to 22. That is this one. Okay, in my cheating slide in front of me, I have this sentence in the beginning of the slide 22. The sentence reads, "This is the most important slide," in capital letters. Stay here for a while. Okay, so this is a very important slide. So I have convinced you that we now should look at the problem and try to reduce the dimension of the problem. Because remember, everything is born from the curse of dimensionality. That fact that I was mentioning to you, the fact that the sample efficiency is epsilon to the power of minus d, this is called the curse of dimensionality. The curse of dimensionality is a term that you will find very often in the machine learning community and also in computer science in general. It refers to several things. There are several instances of this curse, and this is one of them, the most famous in machine learning probably. Then, to reduce this curse of dimensionality, there are several options. Geometric deep learning is just one of them. It's not the best, it's not the worst, I think. And just to be clear, geometric deep learning is not the solution to the war in Ukraine or something like this. But it's just a very nice idea. Another very nice idea that I have a pick to your slides of previous lectures you had told about, I think, is manifold learning. You did this, right? You told about the data manifold and so on. Anyway, manifold learning means that picture of cats and dogs are not really, does not cover the whole 1000 dimensional space. If you take a picture just randomly, filling 1000 pixels with a random color, you will get a noise. Usually, okay, you're very lucky if you get something also just resembling from far away a cat or a dog. So in this picture, the cats and dogs are a lower dimensional manifold. Okay, this could be an approach to reduce the dimension. Geometric deep learning use another information. Okay, now I use this Blackboard. I'm not sure it can be seen in the record. Anyway, tell me this. This is a picture, the frame of a picture. And
now you understand why I studied mathematics and not art. This is a dog. Okay.
So, okay, this is the picture of a dog. Okay.
Let's say you don't know whether this is a picture.
This is a dog or a cat. Okay, and you probably know from this picture. This is true. But now I just take the same picture and I will try to do the same.
And I do this. Almost the same. Now I ask you, what is this? Ask Cynthia.
Dog.
Okay. You are just in the beginning of your training, so I know the real answer. I don't tell you, but I don't care. Now I ask you, what is this? Okay. Francesco. What is this? What is this? Elena. Answer the card, please. What is this? Oh, very nice.
Colpo di scena. Okay, so let's focus on Elena answer. Okay, maybe my picture is not clear, but
can you recognize that
these two pictures are the same, at least in my intention? The same but rotated. Okay. So, why did you answer in a different way?
Make you happy.
Exactly. So, in your opinion, this could have different answers. Do you agree that this is a little bit strange if the task is recognizing whether this is a cat or a dog or no? Okay. So the point is, a neural network in the beginning of the training could answer this way. So good point.
Could answer, this is a cat and
this is a dog. But a human could say, come on, I don't know if this is a cat or a dog because the drawing is awful. Okay, but if this is a cat, this is also a cat. Because at least I can recognize an invariant by rotations, at least of this degree. And so I would say the answer should be the same.
So I would say these are different, but
I'm saying this problem, if we agree on that, and you don't agree on this, and this is perfectly legitimate, but if we agree on this problem should have the same answer, meaning that
if you answer dog here, you should answer
dog here.
If you answer dog, you should answer dog. If you answer cat here, if you
agree on this hypothesis, then
you should answer cat here.
You understand what I'm saying? I'm not saying this is a cat or a dog. And I'm not saying that the neural network will not answer this. A neural network will work this way after training. Why will work this way after training? Because the neural network will have that was shown several pictures of cats with this orientation and several pictures of cats with this orientation. Okay. So now, do you agree that
in this kind of task,
distinguishing picture of cats and dogs, the problem is invariant by rotations?
You also agree?
You also agree?
Okay. So
Okay. So
do you agree also that
this
this
if I
picture
put this picture
completely
this way,
right? Something like this. This is
something
still
like this,
the
this is
same
still
as this.
the same as
Okay.
this.
Also, if this is
Okay.
completely
Also, if this is completely flipped,
this is a
this
dog.
is a dog on his back.
Okay.
It's possible.
It's a strange picture of
It's a strange picture of
So
a
you-
dog, of course. If I show you a picture of a dog, you would expect a dog standing on the ground and the picture in the right position. If I show you this picture, you probably turn it
right?
upside down.
But anyway,
right?
if this is a
But
dog,
anyway, if this is a dog, this is a dog. If this is a cat, this is a cat.
so the task for
So the task of
recognizing
recognizing something
is invariant by rotation.
is invariant by
Okay.
rotation.
And
Okay.
if instead of
And
dog and
if
cats, I
instead
put
of dog and cats, I put
against
against apples and pears,
something changed.
something
No,
changed.
okay. So if I have to distinguish
So if I have
something
to
from
distinguish something,
the in something or not the
the in something or
that
not
something, this
that
problem is
something,
invariant.
this problem is invariant by
So
rotation.
the same for this.
So the same for this.
These two pictures are the same.
These two pictures are the same.
No. Okay.
No.
Well, I don't
Okay.
know if you can
Well,
see.
I don't know if
Yes,
you can
probably
see.
in the
Yes, probably
blackboard.
in the
Anyway,
blackboard. But anyway,
what I was
trying to convince you is that
this
this thing of invariance of the task is very subtle. It's not only the task of recognizing images, okay? It's something more profound. In this case, this is the semantic. We are not, when we say we are trying to recognize digits, we are not recognizing the image of a 6. Because yes, the image of a 6 is exactly the same as the image of a 9. And this is why on every game card, there is a small dot on some part of the card to break the symmetry and allow you to distinguish the 6 from the 9. Okay, so from the point of view pictures, they are invariant by rotation. But when you say the task is recognizing digits, the task is not recognizing the picture of the digits, but the meaning, semantic of the digits.
So this is
okay. So this is just to tell you the importance of the
as was in the
geometry, the importance of what you are looking at, what you are studying, what is the problem you want to solve.
Okay. So
okay. So anyway, if we know that the task we are learning is invariant for a certain group of transformations, this is what I'm calling symmetries in my chatting, then why on the earth we should consider in our model functions which are not invariant?
You understand what I'm saying?
You understand what I'm saying? If I know that the function is invariant by rotation, and then in the model that I will use heavily to choose my function from, the model that I look at several millions of times with gradient descent to pick different functions, the model, the space that I navigate into, I put inside this model which are useless.
Come on, from this point of view.
Come on, from this point of view, it's really absurd, right?
So if I know
symmetries of my problem, it really makes sense to try to not put functions which are not invariant for the symmetry in the model.
Perfect.
Okay, perfect.
So I convinced you that
this is fine, and this is the first important prior in geometric deep learning, the fundamental prior. We want to build models which have this property, as much as possible this property, because we will see this is not an easy property to encapsulate in the choice of the model. Okay, but virtually theoretically, we would like to build a model which contains only functions which are invariant for the symmetries of the problem. And this takes us to another aspect of this problem. So one part is how to build this kind of models. The other part is how to find the symmetries of the problem. Because in recognizing cats and dogs, what are the symmetries? We agreed already on rotations. Okay. And then also, can you imagine other symmetries? Translation, of course, if you move a dog. Translation, of course, if you move a dog in every direction, still a dog. Of course, you are talking about an infinite dimensional picture. Okay, so the dog can move wherever you want. No more symmetries, right? Inversion, okay. Inversion, okay. The right ear is turning to left ear, but who cares? Something else. Something else. So we have all the symmetries.
Scaling.
So we have all the symmetries, right? All the symmetries. All the symmetries. 1, 2, 3. I have a lavalier microphone just to walk around you. So these are all the symmetries. Another symmetry. Relation. Come on, a dog can be cute, or very big. Okay. And I would say also shear transformation in the sense dilation only in one of the two directions. I mean, I can make a dog thinner or thicker up to a certain point, actually. I can't really stretch a dog as much as I want and then say this is a dog. After a certain amount of extent, it will become a dog, right? So you see, right? Finding the complete group of transformation can be local, as I was saying now, the last part, and the complete group of transformations in a task is absolutely not trivial, also in a simple problem like this one. So don't have the false hope to find all the possible transformation of your task. But this is very fascinating because actually it means that we have a lot of space, a lot of possibilities, directions in the direction of every possible symmetry of the problem to move on. So we can try to find as many as we can, okay? And clearly, as more we find transformation, better it is for the problem. So now, the other part of this lecture, the next part of this lecture will be how we can identify symmetries of the problem. And this is taking us to this part of the picture. What is an image? What is an image? An image, a 32 by 32 image is a vector with some positional information, of course, more an array than a vector. But you would say is just a point in a certain vector space, right? Not really. Not really. It is something more. There is another interpretation point of view for images, which is considering an image as a function. An image, interesting point of view, is that it is a function on a grid, 32 by 32. This grid has not colors on the grid, it's just the grid. Okay, it's a finite space with 32 by 32 points, and to each one of these points you associate to one number, which is the intensity of the color in that point. Okay. So this is a function on a domain. What is the dimension of this domain? 2. How can happen? The image has dimension 1000. How can happen that the dimension now is only 2? Well, the image is not this grid. The image is a function on this grid. So what is the dimension of real functions on a 32 by 32 finite space? R2 32 times 52. So it's the same, just another point of view. Okay. But this allows us to find symmetries coming from symmetries of the domain of the function. And in fact, all the symmetries we were talking about, rotations and translations in particular, comes from symmetries of the domain of the function.
What does it mean that you rotate?
What does it mean that you rotate the image? You take the value in this pixel and you put the same value in the rotated pixel. This means that you are rotating the domain of the function and accordingly giving new values in some way, let's say equivariant way. Okay. So looking at data points, what I'm telling you is not only for pictures, it's for everything, also for graphs. Looking at data points, not as points, but as functions defined on a certain domain, opens in some sense the data and gives you new tools, a new point of view to find new symmetries. The symmetries arising from symmetries of the domain of the function. Some terminology. This domain of the function, this omega here in the slide is the domain of the data when you look at the data point as a function. This domain is called the geometric domain. In my talk, the geometric domain will be always a grid because I will talk about images. In Rita, the geometric domain was a graph. Because she was talking about functions on graphs. Because she had a set of nodes and she was looking for properties of the nodes. A property on a node, if it is a scalar property, is a number associated to the node. So a property for each node on the graph is a function on the graph. Okay. Another point, these kind of functions are not always scalar functions. Actually, usually the image has 3 colors, not one. So to each pixel, to each point in the grid, to each point in the geometric domain omega, you associate not one number, but 3 numbers. The red, the green, and the blue channel. So this is a function not in R, but in R3. Okay, this is a scalar function. Okay, so another terminology, the function we are looking at in this sense, since the layer is taking the image as input point and the layer, the neural network is computing a function on images that I'm now telling you are functions. In this sense, a neural network is a function having as inputs a function. This should not bother us since we are mathematicians, it's very common. But to distinguish these 2 different uses of the term functions, the functions of the data points, we will call them signals. Okay, so points, input points to the neural network are signals. And of course, the compositional prior we always have in mind when we use neural networks, the inputs to the hidden layers are themselves data points, and so are themselves signals. So the neural network is compositionally, hierarchically transmitting information under the form of signal, as signals. Okay. So. As I was telling you, this point of view is not only for images. By the way, when I have the output is not one-dimensional, but 2 or 3 or 4 dimensional, I will talk about channels in the output. stealing the terminology from convolutional neural networks that I guess you are already familiar with.
And as I told you,
we can do this also for graph. In this example, the set, the geometric domain is the set of numbers from 1 to n. This is an arbitrary labeling of the atoms in this graph, or the nodes in this graph. And the function is a function in Rm, where m is the number of possible types of molecules that you have, of atoms, sorry, that can appear in this graph, in this molecule. So you are trying to predict in the graph which kind of atom there is for each node. Okay, so to give you a concrete example, completely different from recognizing, distinguishing cats from dogs. Okay, at a certain moment you could also say, okay, I don't care about cats and dogs, I want to solve real problems. Okay, this is more of a real problem. And the setup is exactly the same. Okay. Okay. Now, looking at data points signals, that is functions on R, R2, R3, and so on, is another very nice interpretation. A function on a vector space is a vector space. I mean, not a function. The set of functions on a vector space is tautologically, pointwise, by itself a vector space. Okay, so in this way, images, if you look at them as signals on the grid, it becomes a vector space. Interact with me. You should say, well, but I just told you, in this way, images form a vector space. And you observe, well, images are already a vector space. Images are vectors, right? Tell me. Rita, tell me that images are vector space.
What you want to do is talk about the function, signal versus, the object, the data, and the functions on it. Right?
No, I want you just to let me notice that the images are a vector space, so I can go.
They are vector space, yes?
Yes, you're right, but just images. If you take graphs, graphs are not vector space. But when you look at graphs as functions on the set of nodes, functions with real values, now graphs are a vector space. This is more surprising than images. Okay, next time I should instruct my sparring partner.
No, but no, I think that is an important point. You have the geometric object, and then you have the functions of the geometric object. And that's what you care about.
Yes.
The space and the space of signals. That's a Fourier, moving from one to the other.
Yes, I will not talk about that, but this is important.
Because you guys have studied Fourier analysis, so you know that. So it's moving from the domain of data to the Fourier.
Yes. Yes, signals,
yes.
In fact, they will have a lot to do with Fourier analysis, also with not only Fourier, but more wavelets, if you know what they are. But what I want to say is that looking at data points as signals gives them a lot of additional structure. Now, in certain situations, data points are not a scalar function, but can be seen as a field on some object, particularly on a differentiable manifold, rather than a scalar function. And this is more surprising if you want, but it's not really surprising. You just have to think as f of the, let's say you have a grid, okay?
So f of a point in a grid is the color of that grid. Now imagine that the f of a point in the grid is a 10-dimensional vector. It will happen inside the neural network as soon as you have 10 output channels. Okay, you will have a vector with 10 outputs, and now you can say that this is a vector on that point. So you can say that this is a vector in a vector space that lives over that point. And this is the notion of fiber bundle, vector fiber bundle, right? And so your function becomes a section of this fiber bundle. Of course, for images, this is not really useful, because if you think images are a grid, which is a discretization, a discrete version of the plane. The plane is flat. So when you have a bundle, a 5-vector bundle, this bundle is trivial. And so this is just a function, okay? Because you have a global vector field, a global section, never vanishing, that can give you the unity vector in each fiber. But usually this is not the case. It's the grid you are considering. If you are considering points resulting from a discretization of a manifold with some curvature, then when you turn around the manifold, if there is a non-trivial holonomy, then you will have something strange happening. And it will be useful to look at these vectors as fibers of a non-trivial vector bundle. But this is all on this part. And now we are back to grids, because this is much more difficult to understand. I mean, what I'm telling to you is just the tip of the iceberg, okay? So I'm just trying to let you become curious about the topic, so that you can feel the need and the urge to study all these beautiful things. Okay, this is the definition of what I was telling you. What is a symmetry of the task? I already told you at the blackboard, okay? You have a cut, the symmetry is not of the cut, the symmetry is not of images, the symmetry is not of recognizing cats and dogs. A symmetry is, belongs to a task, is very specific to the task. And what is the task is something very particular. If we want to formalize it in this slide, the task is the label function. Okay, if the label function is true or false for dog, not dog, this is the task of recognizing dogs from not dogs. If the label function is 0, 1, 2, up to 9, then the task is distinguish the 6 from the 9 and from all the other digits. And so this is not the task of recognizing images in the strict sense, because the 6 and the 9 are different. Okay, in the second task, rotations are not part of the symmetries of the task. But notice that you can still rotate a little bit, because you can rotate a 9, right? Maybe 45 degrees. Okay, in 8, you would rotate 90 degrees. Well, if you have the prior that these are digits, then yes. But if you have not this prior and you have to distinguish these symbols, a mathematician would tell you that that symbol is infinite and not an 8. You see how it is important, all the priors, all the hypotheses, to state very well the problem. Okay, anyway, in this formalization, a symmetry is just a transformation of the input data, preserving the label. Okay, and we want to put in our model only functions which satisfy this property, that are invariant under the action of the symmetries. Okay, let me check Now, do you agree that if we know all the symmetries, the course of dimensionality is definitely going away? The answer is yes. And why? So I'm asking you, if I know all the symmetries, I'm saying that I have no problem of course of dimensionality. If I know all the symmetries, for instance here, if I know all the symmetries that are transforming these points to the other points, we have two orbits here, the orange orbit and the purple orbit. My statement is, if I know all the symmetries in this problem, to learn this task, to correctly classify all points that are 6 plus 5, all 11 points of this task, I only need two samples. Which one and why? The prior is that I know all the symmetries, so I can use them. Let's put it this way. If I know the label of this point, and I know the label of this point, yes, but how can I find the label of this point? I know the label of this point, and I know all the transformations. It's a generator, so generate. Take one element of one symmetry. You don't go back. You just take one symmetry, apply the symmetry to this point. Choose another point. It's a symmetry, so we'll take one of this point to another point in the orange. Let's say here. And what is the label of this point then? The same. And now apply, go back here or start from here, apply another element of the group. Now we arrived here. What is the label? Apply all the elements, all the symmetries. You always land in this point. And then you classify all these points. And then start from the other point you have the other label for. Okay, and you cover all the orbit. By definition, you touch all the points because this is the definition of orbit. Okay. So this is what I told you before. Before I told you this with just one orbit. Okay, now there are two orbits. Okay. And I told you before that if I know the symmetries in the domain, in the geometric domain of the data point, I know symmetries on the points, on the functions, okay? And I told you if I rotate an image, this is actually rotating the grid and then taking the new image. Well, this is formalized, but what is called the regular representation on functions. This is a formula that doesn't, you don't need to understand this formula if you know what is the regular representation, but just to let you know, if you have an action of a group on a space and you have a function on that space, then the regular representation is a representation giving an action of the same group on the function on that space. And the definition is this. And it's very clear. You act on the function. How? Well, you act on the input to the function and then you apply the function. Okay, you use the inverse to maintain the right and left action and so on. Okay, now it's time, I think, to hurry a little bit because I want to go to equivariance. Okay, I was telling you up to now, this is another important point. I'm trying to close, okay, to tell you the important part. And up to now, I was telling you that invariance is the important thing. Actually, the most important thing is not invariance, but equivariance. Equivariance means the following. Imagine, focus on the central part of this picture, this one, okay? These are, in particular, the first column. This is a graph with 4 nodes, and this is the image of a function on the 4 nodes, coloring each of the 4 nodes. Okay, so this is a function. Let's say these colors are numbers. Okay, this is a scalar function on the graph made by only 4 nodes. Now, imagine you permute the nodes of this graph. This is something that you have done several times. The graph doesn't change as long as you preserve the connections, of course. Okay, so numbering in a different way, the nodes doesn't change the essence of the graph. The value of the function, this function should be invariant. I mean, the first node was orange. Now, the new first node should be still orange. No, if orange is the right value for that node. Now, orange shouldn't be the first node, but the new permuted node. So if you swap the first and the second node, the new color should be this one. You see, this function is not invariant. When you change the nodes, when you change the points in the domain, in omega, you have to change also the values in the codomain. Okay, you have to swap these values. This vector is now changed. This property is called equivariance. The permutation group that was acting on the nodes, that was swapping the first with the second, this is the meaning of this P12, is acting in a similar way on the codomain, on the value taken by this function. Okay? And a permutation group can act on different sets in different way. In the nodes, it will permute the nodes. In the values of the node, in the coordinates of the vector, it will permute the first with the second coordinate. And you can say, okay, this is essentially the same. But if you are looking, now look at the third part here. If you're looking at the graph with the adjacency matrix, meaning this array with 1 and 0, 1 when there is an arrow, if you permute 2 nodes, if you're coloring the edges now, and not only the nodes, so the colors here refers to the color of the edge connecting 1 with 1, and this is the color of the edge connecting 1 with 2, okay? And if you're coloring this graph, these edges this way, and you are now changing the order of the nodes, this adjacency matrix, these colors of the matrix, this is not the adjacency, sorry, this is the color you're putting on your graph, will change in this way. That if you look at it, it's still a permuted array, but permuted in a non-trivial way. It is permuted by swapping both the columns and the rows. Okay, so the action of the permutation group now is given in this way. You represent the permutation groups on these matrices in this way. Okay, what I'm saying is that the same group can act on different vector spaces in different ways. Okay, now let me skip the Picasso problem. Let's go here. Oh no, just 1 minute. Okay, we'll just show you this this video.
Okay, this is the courses I was suggesting you, and this is, okay, this is an ad, but okay, let me put the face in the right orientation. Okay, now I want to finish telling you how you can build a convolutional neural network which is invariant, not only for translations that you already know it is, okay, convolutions are almost by construction invariant by translations because the same template, the same kernel is translated along the picture. But if you rotate the face here, then the kernel that was recognizing the eyes, the horizontally shaped eyes, will not anymore recognize the same eye rotated, right? So will not activate in the corresponding channel a value corresponding to the eye. Now, imagine that you want to make your network, your layer, let's say, equivariant for rotations of 90, for the 4 rotations, for rotation 90 degree and the other one generated by 90 degree. You can rotate the kernel 4 times, 1, 2, 3, 4, the fourth is the same as the not rotating it, and put these activations in 4 different channels using the same weights. So you are not multiplying the weights, okay? You have 9 weights for a 3 by 3 kernel, the same weights, you just rotate them and you put on the second channel. Rotate them, you put on the third channel. Rotate them, you put on the 4th channel. In this way, the neural network will be able to recognize the eyes, horizontal shape, but also the eyes in the 4 orientations. And you will be able, the next layers will be able to recognize this orientation by looking at the channel. Because they know that the first channel is 0 degree, the second channel is 90 degree, and so on. Okay, in this way, there is much more to say, of course. In this way, you obtain a layer and at the end, a neural network, which is equivariant up to the last layer to rotation and translations. And this is even by this picture. When you rotate, you see, when you rotate the face, this image that you see that is rotating are the activation that are just permuted, are just shifted. For every rotation, they change level. So the effect in the image is that all the 3-dimensional block is rotating. What is happening is just that the levels are going up. And when you reach the last level goes to the 0 level because the rotation is complete and you have, okay, just imagine this kind of thing. Okay, now, last, and I will finish. Let me go to the last layer. As you can see, there was so much more to tell you. These are kind of other kind of symmetries, but geometric deep learning is the following. What I told you is the importance of symmetries, how to recognize symmetries. I have given to you just a sketch of how to build an equivariant layer, equivariant with respect to rotations. You already know a very important equivariant layer with respect to translation, which is the convolutional layer. And trust me, or you already know that if you put one equivariant layer after another, you still obtain an equivariant map. Okay, composition of equivariant maps is an equivariant map. So if you want to obtain a neural network giving a function which is equivariant, you can still do this following the
main prior in deep learning, the compositional prior, that is putting together several equivariant layers. Whenever you want a function which is invariant, because sometimes the problem, cat and dogs, all the problems we mentioned are invariant and not equivariant. At the end, you just collect all the information and you transform all of them in a single information. This will make the equivariant information invariant. And so what I'm saying is that if you want to obtain equivariant function, just use equivariant layer. If you want to obtain an invariant function, just use equivariant layers one after another, and at the end, just concentrate all the information in one single value. This is called global pooling. Okay, just do the operation which is called pooling, which can be done with average, with maximum, every way you like, and you obtain something invariant. If you want, incorporate either other kind of transformation, which we haven't talked about. This kind of transformation are the family that Cinzia mentioned before, that are the dilation, the scale transformation. Then you can do this by inserting another kind of layer, which is a pooling, concentrating all the information in one, but not global, local. So what you already do with the convolutional neural networks, you take points, let's say 2 by 2 points, 3 by 3 points, and you say, I will take the maximum of these activations. Okay, I will forget about the 9 values. I will just take one number, the average, or so on. To give to this technique more representational power, usually this local pooling is non-linear. So it's not an average, it's not a maximum, which is, by the way, not linear, but it can be done also by a neural network by itself. Okay, but this is the concept. This is the geometric deep learning blueprint. That means it's a general recipe to build models which are invariant or equivariant according to the requirements of your task. And I think we can stop here.
We figure this out in a short while.
Okay.
Okay. So unfortunately, we don't have time for questions online. I thank you all, guys.
We tried to speak, but probably you didn't